Today, we are submerging into what is, truly one of the most critical ecological crises facing our oceans, the collapse of the world's coral reefs.
And this is a topic that requires more than just passive understanding, right?
Yeah.
Our sources reveal this dramatic race against time.
It absolutely is. It's leveraging cutting-edge science and engineering, and it's spearheaded by innovators who are focused on actively rebuilding these essential ecosystems, piece by piece.
A million little pieces, almost. Okay, let's just jump right in with the dramatic stakes here. We are facing what our sources call an extinction imperative for these ecosystems.
And that's not hyperbole. The scale of the decline
Oh,
is,
wow.
well, it's staggering, and I think people often underestimate it. The world has already lost anywhere from 30 to 50% of its coral reefs.
In just the last few decades, that's within our lifetimes.
Exactly, and the future projections are, frankly, deeply sobering. Climate models suggest that if we continue on our current warming trajectory, up to 90% of coral reefs could be lost by 2050.
90%.
Which means, without significant, radical, and costly intervention, we are looking at global extinction for these delicate, vital systems by the end of this century.
That trajectory really mandates a fundamental shift in how we think about this. So our mission in this deep dive is to explore the science and, the ethics of moving from passively protecting reefs,
Just protecting what's left.
right, to actively designing them. We're talking about massive technological deployment, things like high-efficiency nurseries designed to speed grow coral, to even radical genetic manipulation.
We're moving beyond just marine protected areas, as crucial as they are for local management. We're looking at these breakthrough technologies and, the new commercial reality, like the story of the man on a mission to reverse this by speed growing coral in these hyper-efficient nurseries.
So for you, the learner, we're providing a clear, detailed roadmap through this incredibly complex and rapidly evolving intersection of science, engineering, economics, and of course, the very tricky ethics of biological design.
It's a huge topic.
It is. So to understand the solutions, we have to first clearly define the magnitude of the problem. Our sources stress that coral reefs are caught in this lethal trap. It's built by two forces working together.
Right, you have global climate change, and then you have the insidious, persistent stress of local human activity.
Let's start with the global piece, the
Yep.
climate crisis. It's overwhelmingly driven by increased CO2 from, well, the usual suspects, fossil fuels, industry, agriculture.
And the most visible and immediate threat from that is, of course, the warming ocean.
We all know the term coral bleaching, but let's go a little deeper into the mechanism. What is actually happening biologically when the water gets too warm?
So, when the sea surface temperature goes above a coral's very narrow comfort zone for a prolonged period, it triggers this massive thermal stress.
And that stress is what causes these mass bleaching events we see on the news.
Exactly. And bleaching is the physical manifestation of the coral expelling its crucial symbiotic algae, the symbiodinium. This algae lives right inside the coral's tissue.
It's what gives it its color, right?
It gives it its color, and critically, it provides 90% or more of its energy supply through photosynthesis. It's basically a live-in power plant.
So the coral isn't dead when it bleaches, it's just starving.
Precisely. It's living on borrowed time on its fat reserves. If the thermal stress goes away quickly, the coral might be able to reacquire new algae from the water column.
But if it doesn't,
But if the stress is prolonged, say more than a week or two, the coral starves to death. And what's left is its white calcium carbonate skeleton. It's a ghost.
and to make matters worse, warmer waters are also linked to an increase in infectious diseases.
Oh, absolutely. It's a compounding problem. Those warmer waters are correlated with increased outbreaks of diseases that often finish off the already weakened, starving coral populations.
And temperature isn't the only chemical stressor related to CO2 emissions. We have to talk about ocean acidification, or OA, which it feels like it's attacking the very foundation of the reef.
It is. Ocean acidification is this profound, silent threat because it undermines the very architecture of the reef. As the ocean absorbs all this excess CO2 from the atmosphere, and we've absorbed about a third of all human-made CO2, that CO2 reacts with seawater to form carbonic acid.
Okay, and that acid does two things, right? It's a double whammy.
It is. First, the carbonic acid releases hydrogen ions, which lowers the pH of the seawater, making it more acidic. But, and this is the really damaging part, those hydrogen ions preferentially bond with the available carbonate ions.
And those carbonate ions are the essential building blocks that corals use to build their skeletons.
They're the bricks in the wall. Corals, mollusks, coralline algae, they all need these carbonate ions to calcify and build their skeletons out of calcium carbonate, specifically a mineral called aragonite.
So by essentially stealing those building blocks, you make it energetically expensive or maybe even impossible for them to grow?
Exactly. We measure this through something called the aragonite saturation state. As OA progresses, that saturation state drops. Corals have to spend more and more of their precious metabolic energy just to precipitate their skeletons in less saturated water.
So what's the result of that? Slower growth.
Dramatically slowed growth. It makes the corals highly vulnerable to erosion from storms, bioerosion from boring organisms like worms and sponges, and just general physical damage. The whole structure becomes more brittle.
And the physical impacts are just compounding that architectural weakness. I mean, we're seeing changing storm patterns that result in stronger and more frequent hurricanes that can literally smash apart these already weakened reef structures.
Absolutely. And then you have more subtle physical effects too. Things like sea level rise and altered currents, which just add another layer of thermal and chemical stress. The reef just struggles to keep pace both structurally and biologically.
Okay, so now let's overlay this massive global crisis with the effects of local human activities. Our sources highlight that these local stressors, they don't cause the global warming, but they critically suppress the coral's natural resilience.
They are lethal cofactors. They're often what determines whether a reef survives a bleaching event or not.
So what are some of the key local culprits that the sources identify?
Well, one of the most critical is overfishing. Specifically, the removal of herbivorous fish species. So think parrotfish, surgeonfish, and also sea urchins.
Why are those specific fish so vital to the reefs? I guess its immune system, so to speak.
They are the essential lawnmowers. They maintain this very delicate balance between coral and algae. If you remove the grazers, then algae, particularly the large, fleshy macroalgae, can just proliferate.
And they take over.
They take over. They quickly overgrow and smother and suffocate young corals, preventing them from settling and reestablishing after a disturbance like a storm or bleaching event. Protecting these herbivore populations is considered, probably the single greatest short-term investment in maintaining reef health.
And then, of course, we have the classic suite of pollution problems.
Right. Heavy nutrient pollution from agricultural runoff like fertilizers and untreated sewage. That stuff just turbocharges the growth of those macroalgae we were just talking about.
The sediment.
And sedimentation from poorly managed coastal development, which literally smothers corals, blocks the sunlight they need for their algae, and clogs up their feeding mechanisms.
And it's amazing, even common consumer products are implicated in this.
Yes, toxic substances. The prime example is sunscreen, particularly ones containing ingredients like oxybenzone.
I've heard about this.
Yeah, they've been shown to directly harm coral larvae and adults, even at very, very low concentrations. And that's why you see certain regions like Palau and Hawaii have outright banned them.
Okay, so let's connect the dots here. The synergistic effect. What happens when these constant local pressures combine with a global heat wave?
This is the crucial biological insight. High levels of chronic stress from these local sources deplete the coral's cellular resources. They're just constantly fighting.
So it suppresses their growth.
It suppresses their somatic growth, their physical body growth, and their sexual reproduction, a process called gametogenesis. They literally have to divert all their energy to just surviving day to day and have none left for maintenance or for making babies.
And why is the suppression of that sexual reproduction, gametogenesis, so lethal for the species' future?
Because it kills genetic novelty. A sexually reproducing population is the engine of adaptation. If a population can't generate new, unique offspring, it loses the ability to adapt to future, different stressors.
So this weakened, resource-depleted state means that when a global threat like a mass bleaching event hits,
the corals are far less likely to survive, and crucially, they're far less likely to recover their population size afterwards. If we can just curb the local stressors, we can essentially mitigate the lethality of mass bleaching.
it's clear that the stakes here go far beyond biology. Our sources really highlight that coral reef restoration isn't just an environmental project, it's an economic and a socio-political imperative.
Absolutely. Just consider the monetary value of coastal protection. Reefs provide this vital natural breakwater. They protect hundreds of millions of dollars of coastal property, infrastructure, and business activity every year from storm-driven flooding.
So the economic benefit alone can often justify the expense of restoration.
In many cases, yes, but the discussion has to also turn to environmental equity.
Of course.
The people most dependent on these services are often the most vulnerable people globally. Reefs protect thousands of people, particularly underserved groups, children, the elderly, minorities, indigenous populations,
We rely on them for food security.
for food security, through small-scale fisheries, and for this critical natural infrastructure against increasingly intense storms. So restoration is fundamentally about protecting human lives and livelihoods.
The situation is obviously dire, but the response from science and engineering is now incredibly aggressive. We are squarely in the realm of active restoration.
Yes, we are.
Let's start with the foundational technique that's used globally, coral gardening. This is all about accelerating biomass production through asexual propagation.
Right. And this method leverages the coral's own innate ability to reproduce asexually through fragmentation. Corals are modular organisms. Unlike us, a piece of the original colony can grow into a whole new, genetically identical individual, a clone.
It's nature's own rapid replication mechanism.
It is, and coral gardening essentially industrializes this natural process.
So practitioners just deliberately break off small pieces.
Correct. They break off small pieces called nubbins from healthy donor colonies. And then these fragments are moved through an intermediate nursery phase. And that step is critical because just placing them directly on a degraded reef yields very poor results.
What are the two main types of nurseries that are being used?
We see in situ nurseries, which are in the ocean itself, and ex situ nurseries, which are in land-based, flow-through aquaria. Both of these systems dramatically improve growth and survivorship rates compared to direct outplanting.
Why is that? What are they being protected from?
Mainly, they're protected from sediment, from predators, and from excessive physical stress during their most vulnerable, smallest stage.
Now, one of the most widely adopted and frankly brilliant pieces of engineering in this field is the coral tree. Tell us about this suspended system.
The coral tree is an innovative midwater nursery. It's so simple in its design. It uses a vertical PVC pipe that's anchored to the seafloor and then held upright by a subsurface float. So it's suspended roughly in the middle of the water column.
And the little coral fragments are hung from horizontal branches.
Exactly, like ornaments on a tree.
What key challenges does that design solve that just putting them on the seafloor couldn't?
Well, three main things. First, it ensures optimal water flow and light exposure, which maximizes growth. Second, and this is crucial, it minimizes their contact with sediment runoff and the seafloor itself, which is where the densest population of predators and diseases often lurk.
Okay.
And third, by being suspended, it often allows for better wave and current action, which some species actually require for optimal growth.
But I mean, suspending thousands of these things in the open ocean sounds inherently fragile. What are the major failure points for a coral tree system, especially when you think about storms or just general maintenance?
That is the operational reality. The main failure point is mechanical stress from storms, particularly big tropical storms that generate powerful deep water turbulence.
So how do they deal with that?
Practitioners mitigate this in a couple of ways. They might use sacrificial weak links in the mooring lines, or if a severe storm is forecasted, they can actually intentionally sink the trees to the seafloor where the wave action is less intense.
And maintenance must be a constant battle.
It's very labor-intensive. It requires frequent diving to clean off algae and remove predators like snails and fireworms. If you don't do that, mortality rates can spike very quickly.
But despite these logistical challenges, the results are pretty significant.
Absolutely. These midwater floating nurseries have proven successful for close to 90 different coral species worldwide. They show dramatically enhanced growth rates and very low mortalities.
And what's the scale we're talking about?
Well, to give you an example, the U.S. Caribbean region alone has over 20 active nurseries, and collectively they provide more than 40,000 healthy corals for outplanting every single year. This one technique has transformed our capacity for active restoration.
So if traditional gardening is the reliable workhorse for branching corals, then microfragmentation is the big technological leap that allows us to target those slow-growing foundational species.
That's the brilliance of microfragmentation. For decades, the massive corals like brain corals and boulder corals, the ones that provide the essential three-dimensional structure of the reef, were largely ignored in restoration.
Because they just grow too slowly.
Way too slowly. Sometimes only a few millimeters per year. They can take decades or even centuries to reach a significant size.
So how did scientists flip that script? What's the mechanism?
It relies on this amazing biological phenomenon. When you cut corals into extremely small pieces, just 1 or 2 square centimeters, it triggers a massive accelerated growth response. It's likely because the organism's repair mechanisms just go into overdrive.
And then they take these tiny microfragments.
And they place them close together, and they fuse. They grow together into a single, cohesive, rapidly growing colony far, far faster than a single colony could ever grow naturally.
So you're essentially generating decades of structural reef-building function in just a few years.
Exactly. This is the key technological jump that has allowed for the commercialization and really the industrialization of restoration. And it's tied directly to the advantage of doing this on land.
Tell us more about those land-based farms, because they seem to represent the pinnacle of this hyper-efficient nursery model our sources mentioned.
They really do. Land-based farms, like the prominent commercial operation Coral Vita in the Bahamas, leverage both microfragmentation and highly controlled environments. By maintaining optimal, stable conditions, perfect water flow, light, temperature, they can achieve growth rates up to 50 times faster than in the wild.
50 times. That's incredible.
It's a game changer, and the stability of a land-based environment must be a massive advantage too.
In what way?
It is the ultimate safeguard. These facilities protect the growing corals from all the acute ocean-based threats, things like pollution runoff, mass bleaching events, and catastrophic storms, which can wipe out an entire in-ocean nursery population overnight.
So it provides a continuous, reliable production line.
Exactly. Continuous, high-volume, reliable production of restoration material. And that is absolutely critical for meeting the scale that's required globally.
But this accelerated production through fragmentation and cloning, it's fast, it's efficient, but it's genetically identical. And that introduces a major critical problem for long-term survival.
It does. You're producing a genetic monoculture.
And that is the hard truth, isn't it? Simple asexual cloning is just insufficient for a climate that is changing at this unprecedented rate.
It is. If you clone thousands of corals with the exact same genotype, they are all susceptible to the exact same new disease or the next severe heat wave. It's putting all your eggs in one genetic basket.
So to truly survive the Anthropocene, we have to infuse genetic diversity and resilience.
Which means leveraging sexual reproduction and, in some cases, some pretty radical genetic intervention.
So how do we get those genetically unique, future-proof individuals?
We have to shift our focus to sexual propagation methods. This means capturing the annual, synchronized spawning events, which are spectacular. Sometimes they only last for a few hours.
And that's when the corals release millions of eggs and sperm into the water.
All at once. So practitioners harvest these gametes, they facilitate fertilization in a controlled lab environment, and then they raise the resulting embryos into what are called planula larvae. This is the tiny, motile swimming phase of the coral.
But then those larvae had to settle and actually survive on the reef. And our sources highlight a major biological bottleneck here.
A huge one. The juvenile stage is the most vulnerable phase of the coral life cycle after that planktonic larval phase. When the larvae finally settle, they face intense competition from fast-growing macroalgae and really high predation from coralivorous snails, worms, and fish.
So natural recruitment is often near zero in these degraded environments.
That's right. So restoration efforts explicitly target this stage. They do things like create specialized settlement tiles and protect the juveniles in the field to maximize their successful recruitment into the adult population.
This leads us into the deepest frontier of intervention, assisted evolution, or AE. This is where we move from passively assisting nature to actively designing for resilience. It's controversial, but it's becoming increasingly necessary.
AE is a radical, direct intervention strategy. It's designed to accelerate natural evolutionary processes, which normally take thousands of generations, to match the pace of current human-driven climate change.
It really shifts the human role from protector to designer of nature.
It does, and that prompts some very serious ethical discussions.
Let's break down the 4 core strategies being explored under this banner of assisted evolution. Let's start with the idea of hardening the corals.
That's stress conditioning, often called acclimation or priming. It involves exposing coral colonies or their larvae to carefully controlled sublethal stress.
So, for instance, slightly elevate temperature or reduced pH.
Exactly. All done in a controlled lab environment.
And what's the biological aim of doing that?
The goal is to induce physiological or biochemical changes that increase their tolerance against future, more severe stress events. It exploits the natural acclimatization processes that happen within an individual's lifetime.
But I read that sometimes, through mechanisms like epigenetics, this acquired tolerance can actually be passed to the next generation.
That's the really exciting part. Through epigenetics, this tolerance can sometimes be passed on without changing the underlying DNA sequence. The environment is changing how genes are expressed, effectively priming the offspring for the stressful world they're going to inhabit.
That's fascinating. Okay, the second approach targets the internal ecosystem of the coral itself.
That's symbiont and microbiome manipulation. Corals and their symbiotic algae, Symbiodinium, form what's called a holobiont, a single biological unit.
And different strains of that algae have different tolerances to heat.
Drastically different. Some are much more robust, so the goal is to give the coral a hardier internal engine.
How do you do that?
Well, scientists aim to modify the coral's microbial communities by introducing these stress-tolerant strains of algae. They often target the early life stages, the larvae, where the symbiosis is first established and is most flexible. If you can get a stable symbiosis with a heat-tolerant strain to take hold, you generate a new phenotype, a coral that can survive higher temperatures.
The third approach feels more like traditional biological engineering, selective breeding.
This is selective breeding or hybridization. We intentionally interbreed colonies that have naturally demonstrated high fitness or resilience, even if they come from different geographic locations.
So you might cross a colony that survived a severe heat wave with one that grew particularly fast.
Precisely. And then there's hybridization crossing closely related species, and that sounds like a risk.
It does, yeah.
It is a risk, but it's a calculated one. Hybridization is done to generate offspring with novel genotypes combinations of genes that weren't present in the pure parental species. The resulting offspring are then grown under conditions simulating the future ocean warmer, higher CO2 to select for the fittest individuals for outplanting.
And we've seen this work.
We have. There's an example of an interspecific Acropora hybrid in the Caribbean that demonstrated equal or even superior fitness to its parents, which suggests there's potential for what we call hybrid vigor in these altered environments.
And finally, the most geographically aggressive strategy, and the one that's currently the subject of the most urgent debate: assisted gene flow, or AGF.
AGS is the managed movement of resilient genetic material-specific alleles between geographically distant populations. It's about taking the genetic blueprints for heat tolerance from, say, a naturally warmer northern reef and strategically moving them to a cooler southern reef.
Buffering those populations against the inevitable warming they will face.
That's the idea.
To understand the urgency behind this, we have to look at the catastrophic, real-world scenario facing Florida's elkhorn coral, Acropora palmata. This is a species that literally built the Florida reef tract, and our sources suggest it is now functionally extinct there.
The situation is beyond dire. The elkhorn coral population has been battered since the 1980s by disease and disturbances. But the 2023 heat wave, it pushed it past the tipping point.
What happened?
Monitoring in the upper Florida Keys showed that the reproductive population of wild genets, so genetically unique individuals, was reduced from 70 to just 13 after that single heat event.
That is a staggering 72% loss of the wild genetic stock in just one area in a very short amount of time.
It's devastating. And what remains are often these small, isolated, monoclonal stands clones that can't mate because there's no genetically different partner nearby. The species is considered functionally extinct in Florida.
Meaning it cannot recover naturally.
Correct. Local extirpation, complete loss from that region, is projected within this decade.
And this presents a textbook example of the ethical and biological dilemma around AGF. Traditional policy dictates we must prevent introducing outside genes.
Because of the risk of outbreeding depression, the fear that the hybrid offspring will be unfit for the local environment.
But the argument is that this is no longer the biggest risk.
Exactly. Experts are arguing, quite forcefully, that this traditional precautionary risk pales in comparison to two far greater near-certain risks. First, the certainty of extirpation if we do nothing. And second, the threat of inbreeding depression.
Inbreeding depression because the remaining population is just so tiny and genetically similar.
Correct. The Florida corals carry a high inbreeding load. Future sexual reproduction from that extremely limited local stock carries a high risk of low fitness and birth defects in the offspring simply due to that genetic similarity.
So introducing healthy, compatible genes from the wider Caribbean is no longer a risk. It's a desperate biological necessity.
That is the argument. The urgent call is to implement AGF now, specifically through lab-based crossing with highly compatible Caribbean corals from places like Curacao or Honduras.
And this managed genetic introduction is seen as mission critical.
It is, to increase diversity and resilience urgently. The operational risks are manageable. You can test the crosses in the lab first, and you only outplant the fit, healthy juveniles. The evidence shows that Florida Curacao elk-horn coral crosses are fertilization compatible, and they produce healthy offspring. Failure to act swiftly and decisively risks losing the species as a functional reef builder in the Florida Keys entirely.
The technological innovations in speed growing and these genetic solutions, they sound incredibly promising. But we have to face the hard truth. Can these methods actually be scaled up to meet a crisis that spans thousands of square kilometers globally?
That is the greatest hurdle. Right now, current restoration efforts, while they're successful in the short term, face major constraints in scaling. The primary issue is efficiency. Current methods are just intensely labor-intensive.
How labor-intensive are we talking? Can you give us a metric?
Even a highly skilled diver might only be able to plant a few hundred fragments per day using manual labor and chemical fixatives. And that rate, hundreds per day, it simply does not scale to the thousands of square kilometers of reef that require intervention and stabilization.
It's too slow and it's too costly.
Are too slow, and there's a real gap in monitoring that makes it hard to prove the long-term effectiveness of the work.
Right. What does the data show there?
Well, we have a significant monitoring gap. Globally, the average short-term survival rate after transplantation is around 66%, which sounds good,
Yes.
but success is often measured only within the first year. Longer-term monitoring is rare, and what we have is worrying. One really important Florida study projected that survivorship could drop dramatically, reaching only 0 to 10% after 7 years.
Wow. So projects that look great for the first year might be ecologically irrelevant over the long term.
They could be. And this suggests we might be restoring accessible areas that are also perpetually doomed to fail due to the underlying environmental stress.
Which brings up what our sources call the site selection paradox.
Exactly. Restoration projects are far more likely to happen in easily accessible areas, so often those with high human influence, like near tourist beaches or ports, rather than remote, pristine areas.
Why is that?
Because accessibility drastically reduces the logistical challenges of monitoring, transporting materials, and ensuring community involvement. The priority shifts from what might be ecologically perfect to what is logistically feasible and has social buy-in.
To combat these limitations on scale, technology is stepping in to transform reef restoration from, a specialized craft into an industrial process.
One capable of volume output. And there are some key technological solutions emerging to close this logistics gap.
What?
First, we have automation. Companies like CoralMaker are focused on developing robotics and automated systems. And these aren't just conceptual. They can process thousands of coral fragments daily, cutting them, mounting them, and preparing them for outplanting. This removes that major labor bottleneck and makes mass production and deployment feasible.
And second, there's habitat engineering.
Yeah.
So you're focusing not just on the coral, but on the foundation it needs to thrive.
Right. We are seeing advanced substrates being designed. This includes proprietary materials like oceanite, which chemically mimics the natural properties of reef substrate to maximize larval settlement.
And I've seen images of the increasingly sophisticated 3D printed reef structures.
Those are amazing. These structures are designed to optimize water flow, light exposure, and create complex refuge spaces necessary for both the corals and the fish species that live with them. They provide the resilient physical foundation needed for a new reef.
And then there are these highly specialized biological support systems like the Underwater Zooplankton Enhancement Light Array, or UZILA. This sounds like something out of science fiction.
UZILA is a fascinating innovation. It's an autonomous, programmable light array that's deployed underwater.
And what does it do?
Corals, as we mentioned, are part photosynthetic, but they are also animals and they need to feed. UZILA uses light to attract and concentrate zooplankton, these tiny microscopic organisms, effectively creating a localized, all-you-can-eat buffet for the corals.
So you're giving stressed corals a powerful, targeted caloric safety net right where and when they need it most.
And testing found that placing corals close to these UZILA lights increases their feeding rates by an astounding 10 to 50-fold.
50-fold.
This massively increased energy intake meets a significant part of the coral's metabolic demand, helping them build the reserves needed to survive that critical period of thermal stress when their symbiotic algae aren't providing energy.
So it's a short-term Band-Aid.
It's recognized as a necessary short-term Band-Aid, yeah. It provides a vital buffer for high-value reefs for a few decades while we hopefully address the underlying global climate drivers.
It really seems like we have the science and the technology, but our sources strongly emphasize the governance barrier. Policy and social failures often constrain success more than any technical challenge.
The science is running ahead of the management. We see major policy gaps, weak legislation, endemic corruption in certain regions, and a profound lack of political commitment to enforcing essential regulations.
So you can plant all the corals in the world.
But if sewage continues to pump onto the reef, or if illegal fishing devastates the herbivore populations, the restoration is functionally pointless.
I have to pause here because that contradiction funding destruction while you're also funding restoration is truly maddening. How do conservationists on the ground even reconcile that emotionally?
It creates enormous tension. They often have to focus on what they can control, the local stressors, while advocating strongly for global change. But the problem is financial.
In what way?
Well, we have innovative mechanisms like the Global Fund for Coral Reefs, or GFCR, which is mobilizing $500 to $600 million in blended finance grants and investment capital to scale solutions across developing nations. This is smart, climate-aware money.
But then you look at the contradiction on the global stage.
Exactly. Our sources cite the egregious example of the U.S. Export-Import Bank providing nearly $3 billion in financing for massive fossil fuel facilities in Australia's Great Barrier Reef World Heritage Area.
So you're funding the problem.
That action actively undermines the climate change mitigation that restoration relies upon and directly threatens the reef ecosystems and protected species. The financial system is simultaneously subsidizing the cause of the problem while funding the desperate solution.
That contradiction just underscores why the importance of local engagement is so absolutely critical to long-term success.
It is the social infrastructure for the physical infrastructure. Community engagement is structurally linked to the long-term viability of these projects.
Basa.
By engaging local stakeholders, incorporating traditional knowledge, and building stewardship, and creating professional roles like the coral gardener we see in places like the South Pacific, you improve social and economic resilience and you ensure sustained maintenance support. No outside organization can maintain a reef for decades without local buy-in.
Let's move from theory and technology to some real-world action. We can start with the Coral Nurture Program on the Great Barrier Reef in Australia. This project is a model for integrating tourism and conservation.
Their mission was dual. First, promote local reef stewardship among tourism operators, and second, build sustainable tourism economies around specific high-value sites that were hammered by those severe back-to-back heat waves in 2016 and 2017.
And their key innovation focused on solving that efficiency problem we talked about, right? How did they drastically speed up outplanting?
They invented the Coral Clip. It's a novel, very simple physical attachment device, essentially a custom-designed nail and strap combination. And it completely removed the need for slow, messy, and temperature-sensitive chemical fixatives like underwater epoxy.
Which takes time to cure underwater.
A lot of time. So what was the practical improvement in efficiency?
I'm curious.
The Coral Clip sped up outplanting by 1 or 2 orders of magnitude. A diver who could previously plant maybe 10 to 20 fragments per hour using epoxy could now plant 100 to 200 fragments per hour.
That's a huge difference.
It is. This speed lowered the cost and increased the capacity dramatically.
And the results showed how these smart partnerships with local industries paid massive dividends, especially when the COVID-19 pandemic hit.
Yes, the resilience was incredible. They established over 50 nursery platforms and successfully planted over 17,000 corals across 6 major tourism sites. But critically, during the COVID tourism downturn, when staff were furloughed and boats were just sitting idle,
The tourism industry was able to pivot.
they pivoted. They leveraged their existing capacity, their trained staff, their equipment, to focus entirely on site rehabilitation. They transformed a devastating economic collapse into a massive restoration opportunity.
That's incredible. Now let's move to the Caribbean and examine the Eco-Design Mooring Project in Dishes Bay, Guadeloupe. This project focused on fixing localized damage while engineering a novel, resilient substrate.
Right, the problem there was severe anchor damage from boats. The solution was to use a nature-based engineering approach. They designed and installed 40 eco-mooring blocks.
And these weren't just concrete anchors.
No, not at all. They were manufactured using principles of green engineering, so they mimicked the natural roughness, the pits, and the small cave shapes that you find in the adjacent natural reefs.
The design was meant to act as an immediate habitat, not just an attachment point for a boat.
Precisely. They optimized the structure to enhance ecosystem integration, and the monitoring showed that prohibiting anchoring and installing these blocks led to a robust return of normal coral and seagrass growth.
And what were the numbers after a few years?
After 6 years, the engineered habitats were fully functional. 52% of local coral species and 43 different species of fish had successfully colonized the blocks.
And how did this engineered solution stand up to the severe weather we discussed earlier?
This is key. These structures were physically robust enough to resist and survive the passage of Super Hurricane Irma in 2017. It demonstrates their value not just as biological homes, but as resilient natural infrastructure that's capable of withstanding future climate events.
The next case study is critical because it addresses that long-term monitoring gap. How do we know these transplanted corals are still there and thriving years later? Let's look at the long-term outcomes in Eilat, in the Gulf of Eilat, Israel.
The challenge in Eilat was maintaining a restoration effort in a localized, degraded area that still faces, unremitting human activities. Their strategy was intensive marine silviculture, so repeated transplantation of hundreds of nursery-bred fragments over a 15-year period onto these denuded reef knolls.
And what was their specific outplanting methodology to make sure those fragments actually stayed put?
They used a specialized underwater drilling methodology to secure the fragments, which was robust enough to allow transplantation even onto vertical faces of the degraded reef structure. This ensured long-term physical attachment.
So what did 15 years of sustained monitoring reveal about the performance of these farmed corals?
The findings were very encouraging. First, the nursery-bred transplants maintained the enhanced, accelerated growth rates that were equivalent to what they saw in the protected nursery environment.
So the conditioning they received paid off.
It paid off. But more importantly, the restored knolls provided new, complex spatial structure and functional habitat for all the coral-associated organisms, the fish, and the invertebrates over that entire 15-year period. It proves that sustained, repeated restoration efforts can yield ecologically meaningful, long-term engineering outcomes.
And finally, we turn to the massive integrated 20-year effort in the U.S. mission. Iconic reefs in the Florida Keys. This is the definition of a large-scale strategic plan.
This project was initiated because individual localized efforts just couldn't keep pace with the systemic decline that followed Hurricane Irma and the devastating stony coral tissue loss disease outbreak.
And the goal is audacious.
It is to restore coral cover across 7 historically important reef sites from the current average of 2% cover to an ambitious average target of 25% cover by 2035.
And they've organized this into specific sequenced phases, right?
Yeah.
Starting fast and then moving toward diversity.
Correct. Phase 1A focuses on quickly restoring the three-dimensional structure of the reef using rapidly growing, framework-building species like elkhorn and staghorn corals to create immediate refuge and complexity.
And
Then, Phase 1B and Phase 2 focus on adding genetic diversity and supplementation with the slower-growing massive species like brain and star corals that provide that long-term stability.
the genius of this plan, though, seems to lie in the recognition that just planting corals isn't enough. You have to fix the foundation of the ecosystem first.
This is the critical integrated lesson. The plan includes active ecological engineering beyond just planting fragments. First, large-scale site preparation. Active removal of invasive and nuisance species before restoration even begins.
And second, and maybe most importantly, the active supplementation of crucial herbivores.
Yes.
Supplementation using what specifically?
They are actively restoring populations of diadema sea urchins and Caribbean king crabs. These species are essential grazers that have seen massive population collapses in the Keys.
So by restoring these herbivore populations, you're ensuring that macroalgae doesn't immediately overwhelm and smother the newly outplanted corals.
You're guaranteeing a higher long-term survival rate and restoring the ecological balance of the whole system.
We've covered a huge amount of ground in this deep dive. We've shifted from the devastating synergistic threats of climate change and local stressors to these highly advanced and at times very controversial strategies being deployed globally to fight back.
Our key takeaway has to be that we have fundamentally shifted from a model of passive conservation to one of aggressive, active intervention.
And this involves combining these established, efficient techniques like coral gardening and microfragmentation.
With major technological and genetic leaps, exploiting tools like assisted gene flow to infuse resilience, automating deployment systems like CoralMaker, and using localized caloric buffers like the UZA light arrays.
But the hard truth remains that the long-term effectiveness of all these technical solutions relies entirely on fixing the governance failures and securing climate-smart, non-contradictory funding to stabilize the local environment first.
Right. Planting corals is useless if we continue to subsidize the source of the heat.
And this entire discussion about the urgent application of assisted evolution forces us into a very heavy ethical space. We are no longer merely passive custodians, we are now the active designers of nature.
It's a huge shift. We have to decide if we are morally obligated to repair the damage we have caused, even if that means moving away from the romantic but likely unattainable notion of restoring some pristine past.
We are optimizing systems. We're forcing evolution to ensure the continued survival of these species and the provision of vital human ecosystem services, coastal defense, food security, tourism revenue. The question is no longer if we should intervene.
But how aggressively and for whose ultimate sake should we be designing this new adaptive nature?
Indeed. And thinking about the scale of this problem and the intensity of the solutions, what stands out to you as the single most critical action we must take right now to secure a future for coral reefs?
Is it the technological innovation of speed-growing corals and genetic manipulation, or is it the political and financial courage required to halt the environmental destruction that makes all that technical work necessary in the first place?
That is certainly a complex ethical and policy calculation. Food for thought for sure. That's all for this deep dive. Thank you for joining us.
Until next time.